new basis. Okay, so we've already done that. We know that if you're given this basis, right? If you're given this basis, you can go from here to this basis. Right? Right? And basically, since these are vectors and these are bases, or these are vectors and these are bases, you can write them some linear combination of these things, right? Let's say, what do you want to call it? Let's say C. And then they will depend on which state you are trying to write, so Jm, and which states, so this is going to be written, this particular state is going to be written as a particular linear combination of some of these states, so which state, and in terms of which ones. So J1, M1, J2, M2. Okay? And these things, as I said yesterday, these things are called Clebsch-Gordan coefficients. And so they are found. You can, for example, find tables of people have already calculated them. You can find tables of Clebsch-Gordan coefficients on the internet, okay, or in your book, or wherever. I'm not going to spend time on them. You just learn how to use them on your own. There are a few theorems that I'll prove about them. Okay, so see, Jm, J1, J2, this is the state. And so this is equal to J1, Jm, J1, J2, right? And then of course I can insert a 1 here, which is J1, M1, J2, M2, J1, M1, J2, M2, and what? J1 and J2 are given, right? J1 and J2 are given, they're fixed. This is 1, this is supposed to be 1, right? If this is equal to this is supposed to be 1. And the 1 is usually the sum over all of the possible eigenvalues or this basis values, right? Which happen to be ortho normal. Okay, what should I write down? What should be the sum over? J1 and J2 are fixed, so it can only be over M1 and M2. Right?
So the second cat,
huh?
second cat का J क्या है?
ये J क्या है? Good question. हाँ जी, ये J क्या है?
अच्छा ये J1.
We've been harping about this J for the last 2 lectures, right?
तो ये J1 plus
ये J1 plus J2 नहीं है. इसकी possible values J1 plus J2 से J1 minus J2 तक जाती हैं. ठीक है? Okay. So if you compare these two, you can just see that this thing is, what is this thing? This is just, yeah, these are just Clebsch-Gordan coefficients, right? Now I'm going to prove a few, well, I'm going to tell you a few things about Clebsch-Gordan coefficients, and then I'm going to prove a few of them. The first thing is that you can choose C's to be real. Second thing is that since the possible values of J were proven, but sort of proven, that they fall between J1 plus J2 and J1 minus J2, then C, J, M, J1 M1, J2 M2. This is non-zero only if J falls between J1 plus J2 and J1 minus J2. J1 is greater than J2. Okay? Then, so J1, M1, J2, M2, this thing, J, M, J1, J2, this is non-zero only if M is equal to M1 plus M2. Okay. How can we show this? This is not difficult to show. Okay, if I were to take this state, Jm, J1, J2, and multiply Jz minus J1z minus J2z, what would this be equal to?
JZ M minus
यहाँ पे क्या लिखूं?
M minus J1Z.
Yes. Anybody?
M1
M1?
minus
Yes. Go ahead.
minus
Yes,
M1
absolutely. No idea what's going on. Yes.
minus M1 minus M2.
So लेकिन ये उसमें state
Exactly. Excellent. Well done for pointing this out that these are not eigenstates of J1 and J2Z. Right? Okay, but I can do something. I can, on the left end, I can dot with this. And now you can, since these are permission operators, you can apply this over here and apply both of these over this side. Okay? And now you would get M minus M1 minus M2. Then you will get J1 okay. J1 M1, J2 M2, JM J1 J2, right? But in principle, you could have given me the answer without doing this by applying this on this. Why? The answer should have been 0, because Jz is equal to J1z plus J2z. So this is the zero operator, right? So this thing is equal to 0. Does it make sense? Right? Okay. So if this thing is equal to 0, then this thing is non-zero only when this is 0, which means this is true. Right? Does it make sense?
Yes.
Okay. Okay, here's another one. More. J1, M1, J2, M2, right? J1, M1, J2, M2. What is this equal to? Yeah. Should be equal to 1. Because M1 and M2 and J2, these are not, these eigenvalues don't form a continuum, right? So it's not going to be a Dirac delta function, it's going to be 1. What is this thing?
So sigma
Delta of
M
Dirak नहीं. This is going to be chronicle delta. Excellent. Very good. This is going to be equal to this, right? Acha. But you can always put a 1 in there, right? How can you do that? So J1, M1, J2, M2, right? And you can put a JM, J1, J2, JM, J1, J2, J1, M1, J2, M2, right? This is okay? Delta M1, M1 prime, delta M2, M2 prime. I'm still missing something. What am I missing? This is not a complete expression. कहाँ पे होगी summation? यहाँ पर किस चीज़ पे होगी?
सर बीच का ऑपरेशन
क्या लिखो? किस चीज़ पे सम होगा?
सर इसको आप अंदर
बाहर लिख दे उससे क्या फर्क पड़ता है?
सम होगा
Again, J1 and J2 are fixed. जब आप प्रॉब्लम शुरू करते हैं J1 and J2 और केवल right? किस पे होगी? J and M. So J और M पे सम, right? लेकिन अगर आप इसको थोड़ा सा गौर से देखें, right? तो इसके बारे में क्या बात आपको नजर आती है खास? अगर मैं इस तरफ 1 कर दूं, M को M1 के इक्वल कर दूं और M2 को M2 प्राइम के इक्वल कर दूं, M1 को M1 प्राइम के इक्वल कर दूं, तो ये क्या बन गया? ये दोनों चीजें एक दूसरे के क्या बना? ये कॉम्प्लेक्स कॉन्जुगेट्स हैं. J1 M1 J2 M2 JM J1 J2 square sum over J. So ये आपको बता रहा है कि अगर आपके पास ये क्लैप्स-गोल्डन कोएफिशिएंट्स है ना, JM J1 M1 J2 M2, अगर आप इनका स्क्वायर लेना और J और M के ऊपर सम कर दें, सारे J और M ले लें जो भी पॉसिबल है किसी M1 M2 के लिए, तो ये आंसर 1 आएगा. Similarly, you can show that कि अगर आप दूसरा रिलेशनशिप देखें जो इसका कॉन्वर्स है, तो JM J1 J2 और J1 M1 J2 M2, इसके ऊपर अगर आप सम करें M1 M2, ये भी 1 के इक्वल आएगा. Right? If you're still in doubt, homework, show this. ठीक है? You will proceed in exactly the same fashion, except आप यहाँ से JM से शुरू करेंगे और जो 1 डालेंगे वो इन स्टेट्स का होगा, right? And then you will have a sum over M1 and M2, and that will prove it. हाँ, जो भी चीज चेंज हो रही है उसी को पसंद कर सकते हैं ना. Let's not go there. You want to say that these are vectors and the transformation between them should be tensors, and somehow you're in sort of
index
maybe हाँ ठीक है, गलत नहीं है. So basically a transformation matrix. अच्छा, इसी नोट पे अब देखिए, अगर आपको मैं वो दो स्पिन हाफ वाले सिस्टम पे ले चलूँ तो क्या था, आपके पास ये स्टेट थी ना 1 1 1 0 1 -1 and 0 0, राइट। और दूसरी तरफ स्टेट थी आपके पास प्लस 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 और प्लस माइनस माइनस प्लस और माइनस माइनस, राइट। अब इनमें से कोई भी स्टेट इनका लीनियर कॉम्बिनेशन थी, राइट। सो देयर मस्ट बी समथिंग लाइक दिस कि आप यहाँ से कोई भी स्टेट ले लें, इनका लीनियर कॉम्बिनेशन बनाएंगे तो आपके पास यहाँ मैट्रिक्स आ जाएगा, राइट। वो मैट्रिक्स क्या था, वो मैट्रिक्स ये था right? Now you can interpret these results. आप कोई सी भी स्टेट ले लें, अगर आप F1 F2 के ऊपर सम करेंगे तो ये स्टेट्स इसके लीनियर कॉम्बिनेशन में मिले, स्टेट का लीनियर कॉम्बिनेशन ये स्टेट जनरेट करेगा। वो कहाँ से आएगा, ये सारी होंगी, इन सब का स्क्वायर करें और ऐड कर लें, हर रो आपको 1 देगा, ठीक है। अगर आपने इनवर्स निकालना है तो उसका मतलब सारे कॉलम्स का स्क्वायर करके ऐड कर लें, वो भी आपको 1 देगा। जिस तरह से आप ये इन स्टेट्स को इनके लीनियर कॉम्बिनेशन में लिख सकते हैं, इसी तरीके से आप इसका इनवर्स निकाल लें तो इनको इसके लीनियर कॉम्बिनेशन में लिख सकते हैं, राइट। So any questions? So that's what I have to say about Krebs-Gordon coefficients. You can find more about them in your book, but I would like to start with scattering theory. So we've skipped perturbation theory for the time being, and so I'm going to come back to it. I'm not sure how much time we'll have left for it, but I'm sort of guessing that you guys already had good practice in perturbation theory, but usually it's the scattering theory which is lacking. So every time we do the perturbation theory first and then the scattering theory, and what happens is that we're only left with a couple of lectures, and those we can't just go very far. And so I'm going to sort of finish with the scattering theory now, and then if we have time left for a couple of lectures, I'm going to talk about perturbation theory in the end. And I'm going to go very fast through it, but I'm sure you guys are not going to mind because you already know it. Because this is one aspect of perturbation, quantum mechanics that you guys have very good command of, this calculations, perturbation. Anyhow, so what do you understand by scattering? Let's say classical scattering. Right. So for example, one-dimensional scattering. Reflection in many directions. Reflection in many directions. Yeah, you could say that, scattering into many directions, fine, but I'm talking about one dimension.
The interactions with
In one dimension, you will either have reflection or transmission, right? So basically, something like you have a target and you have a projectile, right? And so you hurl this projectile at this target. But the special thing about this is that you know the momentum, right? So this has a definite, so you exactly know what momentum it has. Of course, since classical mechanics, you know what the position is, but you're more concerned about the momentum, okay? So this has a certain momentum, and then at some point, so it's basically free. There are no interactions, and for a very small amount of time, there is a very strong interaction. We call that scattering, right? If you're in one dimension, basically, depending on the mass of these two objects, whether this object will sort of go in the forward direction or it will come back in this direction. This is what your concept of classical scattering is, right? And using conservation of momentum, and if it is elastic scattering using conservation of energy, you can describe exactly what is going to happen given the two masses. Okay? What about quantum scattering? So,
potential then, it will have to pass through potential barrier.
right. So for target, you'll have let's model this target with a potential difference, right? Let's say that we just change the potential in this region. So at x is equal to 0, the potential is 0 here, and on this side you have a finite potential, right? So there's a jump in the potential. What else? Should I take a particle and then just throw it at this target?
It will be a wave function.
It would be, why would it be a wave function? Can't I talk about a particle? If I can't talk about a particle, then what do I know about the system? I mean, it would be a wave function. What do I know about that wave function? You want the picture to be, if you want the picture to be something like this, that initially there is no interaction. And then at some point there's very strong interaction, and then either the particle reflects or it goes through. Right? Something like that. What would be the corresponding picture in quantum mechanics? Of course, that's absolutely correct. That you would have to, if you want to sort of take this picture, then you would have to replace this thing with a wave packet. Right? Why? For example, why can't I put it in an eigenstate of position?
Because it has a momentum and its position is
I can put it in an eigenstate of position, that's not a problem. I can make this, let's say if this is the Gaussian, then I can just make the width go to 0, and then the particle will be in an eigenstate of position.
So, but if we know the momentum certainly, then we will have to be able to.
If we know the position certainly, then, not the momentum, if we know the position certainly, then the momentum is completely undefined, right? And so we don't know what is happening. We can't have a picture like this, right? On the other hand, if you put it in an eigenstate of momentum, then what happens?
But then we can compare the momentum and the corresponding energy with the potential of the barrier. So we can know if the energy of the particle
Okay, what does
is
the,
greater or less.
so I just told you what the eigenstate of position looks like. What does the eigenstate of momentum looks like? For a given momentum, let's say T naught. What does it look like? We've calculated it.
Plane?
Yes, the plane wave. And the plane wave, where does the plane wave start and where does it end? Where does the plane wave start? Minus infinity, where does it go?
Towards the barrier.
Towards the back. It exists for all time and for all space. Right? Right? This is a one-dimensional problem. So it is going to be something like this. And now your picture that you have a particle somewhere and it is not interacting, and then at some point it does interact, and then there is a reflection or a transmission. That is ruined. Because this has no end and no beginning. It exists for all space and all time.
So if we had an eigenbasis of position, then wouldn't it have...
Second?
If it was the eigenspace of position,
Right, right.
then wouldn't we have a plane wave?
Oh, Okay, yeah, good question.
Well, then would be the
Then we
space.
would have a plane wave in the momentum space, but not in the position space. So how do you describe the, if you're not convinced, how do you describe the eigenstate of position? What is the wave function? So this is the eigenstate of position, right? What is the wave function?
So e raised to power minus 5 raised to delta.
No.
x.
No.
Sine. Sine.
This is the wave function. It's a delta function. And a delta function can be modeled as a Gaussian of zero width. Almost zero width. Right? So then it will not be like this. It will be a spike somewhere. But you wouldn't know where it's going.
It will be just in one state
It will just be in one state.
of x. So it will be stationary.
Ah. What do you mean by stationary?
Yeah, I mean, if it's an
Aren't these
state of x, then it would be just on one fixed point of x. That's where it's.
Yes, that's how you prepare the state, right?
Yeah.
So it's an eigenstate of position, but you don't know anything about the momentum.
But if it
The momentum could be anything between plus and minus infinity.
Yeah, but the position would be just the same. It would be.
But that's exactly the classical thinking that you're stuck with again, right? You want to say that I have prepared the system in an eigenstate of position, right? And so it better be there when I look at it again. It shouldn't be going anywhere, quote unquote. So the momentum must be zero. Right? That's the problem with it. That's not true. Anyhow, we're not going to be bothered by the eigenstate of position, right? Because we don't know about the momentum then. What would we ideally like is to put the particle in an eigenstate of momentum. But then, what we're left with is this. So we want to make the system as classical as possible. So what do? We make a wave packet. And the most classical system is where the uncertainty in position, the product of uncertainty in position and momentum has its minimum value. And that wave function is? And that wave function is a Gaussian. Right? Gaussian satisfies delta x, delta p equal to h squared over 2. Okay? So anyhow, so the picture now becomes that far, far away from this position, you have a Gaussian somewhere. Let's say at x equal to minus 8, initially. Right? So you know that's a probability, probability sort of concentrated within the few standard deviations. Right? And on both sides it goes exponentially off, right? And so, but you still don't have this clean picture. Why? Yeah, fine. But this wave function is defined for all space, right? There is no cutoffs on it. You don't just cut it off something. So it has sort of, it already has seen that it sees the whole space, sort of. But it already knows that there is this value. It just, the whole of it, the bulk of it hasn't reached it yet. Okay? So it's not like the particle doesn't know anything and then suddenly it just comes and hits the other target, and depending on the mass, whether it goes through or comes back. Right? So, if you wait for a very long time, so if you give it an average momentum of p naught, let's say, the average velocity is going to be p naught over m, right? And if this distance is A, then this is the approximate time in which this will come and sort of quote unquote hit the target. Right? And if you wait for a very long time after that, then you will have, if you're lucky, if you can arrange things so that one wave packet will be going this way and one wave packet will be going that way. And the area under this will give you the probability of reflection, and the area under this wave packet will give you the probability for transmission.
A divided by T naught क्या है?
T naught जो है हमने इसका एवरेज मोमेंटम दी, right? इसकी एवरेज पोजीशन जो है वो ये है initially. So this is initially, sorry, ठीक है, वो तो गायब हो गया, initial वाला तो गायब हो गया, right? So आपके पास एक wave packet था जो अंदर जा रहा था. So this is for time. So initially, again, let's take one more picture. Right? So ये initial है. This is the initial situation, and after a very long time, you can say that this is finally how it looks like as t goes to infinity. And so this is your initial Gaussian, and then this is the reflected wave packet, and this is the transmitted wave packet, and this thing is basically the coefficient of transmission. And this thing is the coefficient of reflection. And you know that T plus R has to be equal to 1. Probability is concerned. Particle has to be somewhere. Does it make sense? So this is what we're going to do. This is how we're going to proceed. We're going to take an initial Gaussian. This is going to be a wave packet. This is going to come, and then, this is the qualitative picture. It's going to come and strike, blah, blah, quote unquote, strike the target. And we will try to identify these two wave packets in this condition. Does that make sense? Okay, so this was all, yes?
So after that, the particle has already seen the value, even if it is a long way
Yes.
off. So why do we have to put the condition that T is greater than T naught? If it's already
Because
seen it, then
I'm just sort of comparing it with the classical picture, right?
so
Right.
in quantum then
But in any case, if this is far, if this is let's say 1,000 standard deviation away from this, then all of the probabilities just within let's say the first 10 standard deviations. So the particle has seen in sort of very vague way this, but the wave packet has still not had a considerable interaction with the target,
so at
with the
least
step potential.
if the particle is originally very a long way off from the value, then at T equals to 0, we won't be able to have both the reflected and the
Yes.
incident.
You would have something like that, very small things, but you won't be able to identify them cleanly. Only in this limit do you hope to see something very far away from the step potential on this side, and something very far away from the step potential on that side. And now, since these two have completely sort of gone their ways, now you know what the reflected part is and what the transmitted part is. These are going to be Gaussians as well, and if you're close by, one will look like this and the other will look like this, and they will have large overlap, and you won't be able to sort of identify them cleanly. Okay? So you have to wait for a very long time before you can sort of, again, let's say 99.9% of the probability is on this side, and the 99.9 probability of this thing on that side. Right? Something like that. I mean, again, so this picture is not going to be clean as it was in the class picture. So this was all good, the qualitative discussion, but how do you sort of do these kinds of things? So when I say we will evolve the wave packet and blah blah blah, and the wave packet will come and strike the target, how do you do that in quantum mechanics? You know what happens in classical mechanics, you just have to sort of run with the conservation laws, right? So momentum is conserved, and if you have elastic collision, then kinetic energy is conserved, and you can just work out everything using that. Whatever happens during the collision, you just don't talk about, right? How objects sort of deform and store elastic energies, and then they come back or lose some of the energy in heat or sound. You don't talk about that, right? So, what do you do here? How do you do all of this scattering? Well, just like any other quantum problem. You're given an initial state, which is this. You know how to evolve this in time. You're given psi I. Psi I is a function of x at time t equal to 0, right? And then you work out u, t, x prime, t prime, apply there, and then you get psi of x of t. And psi of x of t, you try to identify these two pieces for t very large. Does that make sense? So, let's do this step by step. What is the first step that you will do? Since you have to identify, since you have to construct this, what is the first step that you do? How do you construct U? In fact, you don't have to actually do this. But this is in principle what we're doing. जो भी हैमिल्टोनियन होता है उसकी आइगन स्टेट्स निकालते हैं. जो भी हैमिल्टोनियन होता है उसके आइगन स्टेट्स निकाल देते हैं, राइट? क्योंकि हमें ये पता है कि हैमिल्टोनियन की आइगन स्टेट्स को अगर हैमिल्टोनियन टाइम इंडिपेंडेंट हो, जैसे कि यहाँ पे है कि हैमिल्टोनियन इज टाइम इंडिपेंडेंट, राइट? Then you exactly know how to evolve the eigenstates of Hamiltonian, right? So you've been given this psi of I, you find out the eigenstates of Hamiltonian, you expand this as a linear combination of the eigenstates of the Hamiltonian, and then you know how to evolve them in time. That part that she's talking about, e to the minus I e t over h cap, right? Okay, so the first step, so let me just write these down again. Write these down again. We've done this many times, but step one is, okay, so find the eigen functions or eigenstates, in this case eigen functions because we've been given wave functions. So eigen functions of h, right? And what is h? And p squared over 2m plus v, and this v is v naught for x greater than 0 and 0 for x less than 0. Right? What is step 2? I just described all the steps. What is step 2? You want to find out psi I as sum or integral, whatever it is, of let's say, okay, so you can write it like this, psi I, and then the wave functions of this are, let's say, psi of k, and so there will be some eigenvalue here, psi of k, right? we'll have to still find them. And so this will be sum over k, psi of k, psi of k. So you have to find these. What are these? Let's call them A of k or A of e. Right? So you have to find these. Then what is step 3?
So we can write psi I as a series of A k psi k.
Whatever? Yeah, yeah, go ahead. Sorry, I didn't hear.
So we take psi as a series of A k and psi k and find the energy of psi k.
Well, we already know what the energy is here. We've already done that. These are sort of free particles on both sides, so the energy is going to be something like h cut square k square over 2m. Right? Well, now since you know these, you know what AE of or AK of T are. They are just AK e to the minus I EK P of ever h cut. Maybe that's what you were saying. Right? Which means that you know what psi of x t is now. Right? It's just going to be whatever sum AK of t and psi k. Right? So, find the eigenstates of the Hamiltonian, expand, evolve in time, and then the final step is, what is step 4? What is step 4? Identify psi r and psi t in the limit t going to infinity. That's what you have to do. 4 steps. Questions? Okay, so there are going to be a lot of integrals involved, and I'm not going to do them. All of this discussion, although I'm going to sort of solve the first step quite thoroughly, but the rest of the discussion is just going to be complicated. A bit convincing. Anyway, so let's start. Step 1. What do the wave functions, what do the eigenfunctions of the Hamiltonian look like in this region? Shabash. So psi is e to the I k1x or e to the minus I k1x a b, right? Right? What is k1? K1 right? Because energy is just h cut squared k1 squared over 2m. Okay. What does the wave function look like in this region? So let's write x less than 0, x greater than 0, or you can count them side 1 and side 2, whatever. By the way, since this is k1, I'm going to write k1 here.
C is for k2x.
Yes. C e to the I k2x plus d e to the minus I k2x, where k2 is right? And we're talking about, since अच्छा एक और बात है यहाँ पे बहुत important मैं भूल गया. I should have talked about that. The energy of this thing, right? If you're talking about the wave functions or the eigenstates of the Hamiltonian with energy less than V naught, right? Then in this portion they will be exponentially decaying, right? Here there will be plane waves, but here on this side there will be exponentially decaying. So we're not talking about it. Because we want, in the limit t going to infinity, we want something transmitted that goes to infinity. This will not go to infinity. Okay? For completeness, we should include these in your these things here, but they will not contribute to the final result. So I'm talking about when E is greater than V naught. Those are the things. Okay. Fine. Fine. So how do you determine A, B, C, and D?
So by line establishing of the boundary.
Okay. So this thing on the right hand side, you don't want any wave packet that is you don't want any wave, stationary wave, which is moving to the left. Right? So this thing is 0. Does it make sense? So let's just get rid of it. And then, as you guys said, exceptional, you just match psi and psi prime at x equals 0. Right? And that gives you, and I'm just going to go through this very quickly, that gives you A plus B is equal to C, and you guys can do this on your own. A minus B, this is just a derivative, ik comes out, minus ik comes out, so ik A minus B is ik to C, and now you have two equations for three coefficients. So what do? That's how it should be actually. That's how it should be actually. Why? Because the overall constant is not to be worried about. Right? So if you can just determine A and B, that ought to be enough. So in fact you can determine, by the way, you can see that this is the incoming wave. This is the reflected wave. And this is the transmitted wave. Right? So basically you want to write both of these in terms of that. But this is the thing that you sort of prepare and it's coming towards target. And so you just, if you can just give me B over A and C over A, then you're fine. And B over A and C over A are, so B over A is K1 minus K2 over K1 plus K2, and C is 2K1 C over A. This is 2K1 over K1 plus. Right? And if you want, you can write them in terms of energy as well. This is E to the power 1/2 E minus V naught to the power 1/2 over blah blah E to the power 1/2 plus E minus V, and similarly for this. Okay? So now, if I wanted, let me erase these, I can write the eigenfunction. By the way, you can see that this K2 is also, as I just wrote down, this is just, this can be written in terms of K1 as I did not write this down. K1 squared minus 2mv naught over h times squared. K2 is just this. So, both of these are K1, right? So, I can write psi of K1 of x like this. A e to the I K1x plus b over A e to the I K1x theta of minus x plus c over A e to the minus I plus I K2x theta. Right? And if you remember our earlier discussion, we know that this is 1 over 2 pi. Okay? The normalization for these kind of things is 1 over 2 pi. And you could have chosen this to be anything. What actually means is what these things are. कैसे लिखें इसको? इसको कैसे लिखें? अब मैंने सब कुछ ये खत्म कर दिया, x greater than 0, x less than 0 की जगह ये थीटा फंक्शन का स्टेप फंक्शन डाल दिए, राइट? सो लेफ्ट हैंड साइड पे वेव फंक्शन इस तरह से, राइट हैंड साइड पे इस तरह से है, और हमें पता है कि c over a और b over a ये है. I'm just not writing them out explicitly. हाँ, ये K1 किसी एक K1 के लिए है ना, कोई भी एक सॉरी क्या कर? हाँ, तो K2 खुद K1 का फंक्शन है ना, राइट? अगर आपको K1 पता है तो आपको K2 भी पता है. Okay, step 2. What do you want to do now? We have to calculate A of K, A of K1, right? So you have to calculate A of K1. So that is going to be equal to 1 over 2 pi minus infinity to infinity e to the minus I K1x psi I of x dx. Handy. What is, I have sort of cut down on something. Can you see what is happening? Is this right? ये ठीक है? अगर आपको ये पसंद नहीं आया और लिख देता हूँ. Let's get rid of this. अगर आप तो फिर इसको आप ऐसे लिख लो. E to the I K1x plus b over a star e to the I K1x theta of x and then psi I of x plus 1 to infinity 1 over 2 pi e to the I K2 of x theta of x psi I. And the claim is, अब दोबारा लिख देता हूँ, कि this is e to the minus I should be minus I K1 of x psi I of x dx. Just a second. हाँ जी, अब बताएं क्या कह रहे हैं? इस पे तो कोई इतराज नहीं है ना? इस पे क्या इतराज है? यही स्टेट निकाली है ना आपने, वो साई K1 है ना। तो आपने AK1 क्या है, इनर प्रोडक्ट है साई K1 और साई I का, राइट। साई I लिख दिया, साई I को ऐसे लिख दिया। अगर आप चाहें तो साई I भी दिया जा सकता है, psi I, maybe I should write that down as well. So psi, for definiteness, I'm not going to be using this for integration. It's just pi delta squared 1 over 4 minus e to the I k naught x plus a, right? E to the minus x plus a squared over 2 delta squared. Acha. If you want to be very close to the classical picture, you want this to be peaked in the K space at K naught, right? In fact, इसका अगर ये आपके पास हो तो ये क्या चीज है, ये किसके इक्वल है? minus a, right? अच्छा, और डेल्टा x किसके इक्वल है? ये आप लोगों ने एक्सरसाइज की हुई है पहले। और p किसके इक्वल है? k star, right? And you want this, if you want to be close to the classical picture again, right? Then you want this to be peaked at K naught. This is a very important point. ठीक है, आप चाहते हैं कि ये पीक हो K naught पर, और डेल्टा P क्या है by the way? डेल्टा P होगा 1 h cut over square root of 2 डेल्टा। अब यहाँ से देखें, यहाँ से आपको पता लगेगा पीक का मतलब क्या है। जब कहते हैं कि इसको पीक होना चाहिए K naught पर मोमेंटम स्पेस में, उसका क्या मतलब है? इसका मतलब है डेल्टा P should be very small, which means delta should be very large. If delta is very large, then delta x is very large. ठीक है? आप दोनों चीजें नहीं कर सकते। अगर आपने अनसर्टेनिटी मोमेंटम कम करनी है तो पोजीशन में ज्यादा करनी पड़ेगी। ठीक है? गाउसियन लिखा है, एक ऐसा गाउसियन लिखा है जो इस तरह मूव कर रहा है, राइट? दो एवोल्यूशन होती है ना, एक तो आपके पास गाउसियन वेव पैकेट है, वो खड़ा खड़ा डिसॉल्व हो जाता है, डिफ्यूज हो जाता है, राइट? और दूसरा है कि वो साथ मूव भी कर रहा है, उसका जो सेंटर है वो मूव कर रहा है, राइट? हाँ जी, are we on the same page? अच्छा, आप यहाँ पर वापस आ गए। अब क्लेम ये है कि this thing is approximately equal to this। वो कैसे? वो यहाँ पर मैंने यहाँ पर C over A भी है, यहाँ पर C over A स्टार।
ये K dot और K1 K dot और K1 different है।
K dot और K1 different है।
K dot initial।
और K dot क्या है?
सर वहाँ पर जाके साइबान में
K naught और K1, हाँ, तो यही तो, ये K1 जो है ये तो कुछ भी हो सकता है। इनफैक्ट ये K1 ऐसे भी हो सकता है कि इसकी कॉरेस्पॉन्डिंग एनर्जी V0 से कम हो, ये भी हो सकता है, राइट? उस डिस्कशन में मैं नहीं जाऊंगा, लेकिन आपको नजर आ रहा है कि उस सूरत में इस साइड पे आपको कोई भी रिफ्लेक्टेड चीज नहीं मिलेगी, एवरीथिंग विल बी ट्रांसमिटेड चीज नहीं मिलेगी, एवरीथिंग विल बी इवेंचुअली रिफ्लेक्टेड, राइट? So that's not a very interesting state to consider. बात समझ आ रही? अब आप इनर प्रोडक्ट ले रहे हैं। बेसिकली अगर आपने ये डेल्टा बहुत बड़ा लिया हुआ है और आपने इसको इस के पे पीक किया हुआ है, तो ये आपने गॉसियन बनाना कैसे है? बेसिकली ये जो प्लेन वेव्स हैं उनका सम होगा ना जो गॉसियन देगा, इसमें कई प्लेन वेव्स होंगे, लेकिन सबसे ज्यादा वो ये तकरीबन वही प्लेन वेव कंट्रीब्यूट करेगी जो के नॉट पर होगा, राइट? जिसका मतलब है कि बाकी चूंकि ये सारी चीजें के और के प्राइम जो है दिस इज जीरो इफ के इज नॉट इक्वल टू के प्राइम, राइट? तो ये K1 ये जो K1 ये क्या है? ये है राइट, ये है लेफ्ट मूविंग वेव और ये है राइट मूविंग वेव, सो दे शुड बी ऑर्थोगोनल टू ईच अदर। सो ये वाला इससे कंट्रीब्यूट नहीं करेगा। ये बात सब नजर आ रही है? यू डोंट हैव टू डू द इंटीग्रल टू फाइंड दिस आउट। अगर ये शार्पली पीक्ड है के नॉट पर और ये राइट को मूव कर रहा है, ये लेफ्ट को मूव कर रहा है, दे आर ऑर्थोगोनल टू ईच अदर, तो दिस विल गो अवे।
अगर वो के नॉट पे शार्पली पीक नहीं है इन गॉसियन,
हाँ, फिर आपके पास दूसरी चीजें क्यों होंगी?
सर लेकिन तब भी वो ऑपोजिट डायरेक्शन में मूव कर रहे हैं।
नहीं, फिर आपके पास हो सकता है कि ऐसे उन चीजों का इसमें असर मौजूद हो जो लेफ्ट की तरफ भी मूव कर रहे हो। आपको दोनों किस्म के जोड़ के तो ये बनाना पड़ेगा ना। आपने इसको स्पेस में
जीरो पे सेंटर से नेगेटिव के पॉजिटिव के
दोनों मिलके इस तरह की कोई चीज बनाएंगे ना, बल्कि तकरीबन हर चीज मिलके इसको बनाएगी, हर चीज का नॉन जीरो कंट्रीब्यूशन होगा। लेकिन हम ये कह रहे हैं कि क्योंकि इसको हमने बहुत बड़ा किया हुआ है पोजीशन स्पेस में, इसका मतलब है मोमेंटम स्पेस में वेरी शार्पली पीक्ड है, सो सब चीजों का जो भी इनर प्रोडक्ट होगा तकरीबन जीरो होगा एक्सेप्ट जो एग्जैक्टली के नॉट है, ठीक है? सो ये एग्जैक्टली जीरो नहीं होगा, लेकिन दिस विल बी, अगर आपने इस वेव फंक्शन की वही प्रॉपर्टीज रखी हैं जो वहां पे लिखी हुई है, देन दिस विल बी ऑलमोस्ट जीरो, नेग्लिजिबल, व्हेन बिकॉज दिस इज लेफ्ट मूविंग एंड दिस इज राइट मूविंग, ठीक है? अच्छा, ये जीरो क्यों होगा? ये तो राइट मूविंग है, ये भी राइट मूविंग, ये जीरो क्यों होगा? बल्कि ये ज्यादा जीरो होगा। नहीं, K1 की वैल्यूज तो हम ऐसी ले सकते हैं जिसमें वो K नॉट इक्वल आ जाए, K2 K नॉट इक्वल आ जाए, ये इस वजह से जीरो होगा। इसकी सारी सपोर्ट जो है, ये चीज है कहाँ पे? ये चीज सारी यहाँ पर है जहाँ पर थीटा ऑफ x जीरो है, और ये थीटा ऑफ x नॉट जीरो यहाँ पर है, ठीक है? So basically these two will not contribute and you will be left with this. लेकिन ये चीज है क्या? ये चीज क्या है?
रिफ्लेक्टेड वेव,
ये ट्रांसफॉर्म है साया का, और ये आपने कैलकुलेट भी किया होगा। दिस इज अगेन अ गॉसियन व्हिच इज डेल स्क्वायर्ड ओवर पाई 154, if you want I can write it out, K1 minus K naught square del square। और आप यहाँ से देख सकते हैं कि जब आप K नॉट से दूर जाएंगे तो कितना शार्पली ये डिके करेगा। तो ये वो एम्पलीट्यूड है जो आपको बताता है कि आपको कौन से K वेक्टर्स मिलाने हैं इस चीज को बनाने के लिए, कौन सी प्लेन वेव्स आपको जोड़नी है, कौन सी प्लेन वेव्स आपको मुख्तलिफ वेट्स के साथ जोड़नी है ये गॉसियन बनाने के लिए, राइट? ये उनके वेट्स हैं, राइट? तो आप देखते हैं कि जैसे ही आप K नॉट से दूर जाना शुरू करते हैं, तो अगर तो ये शार्पली पीक्ड है तो फिर यानी कि डेल स्क्वायर बहुत ज्यादा है, अगर डेल स्क्वायर बहुत बड़ा है तो जैसे ही आप K नॉट से दूर जाएंगे ये बहुत तेजी से गिरेगा, ठीक है? Does it make sense?
सर आप बता सकते हैं जो K1 पॉजिटिव K1 वाला वो ऑपोजिट डायरेक्शन में जाने की वजह से जीरो देगा?
कौन सा ये वाला? हाँ, ये लेफ्ट मूविंग वेव है और ये राइट मूविंग वेव एंड और ये दोनों अगर डिफरेंट हो ये जीरो होता है, राइट? अगेन द आर्गुमेंट heavily relies on the fact that this is sharply peaked in the momentum space at k naught. अदरवाइज यहाँ से आप देखिए अगर डेल बहुत छोटा हो तो आप दूर भी जा सकते हैं k से, फिर ये बहुत जल्दी नहीं गिरती, ठीक है? डेल को बहुत बड़ा होना चाहिए। ठीक है? ओके, सो स्टेप 3 अब आपको क्या करना है? psi of x t लिखना है, right? That will be equal to what? Minus infinity to infinity. Yes, let me write it down. Yeah. So psi x t is this ये चौक ठीक है? ठीक है? Let me just write it out and then if you have questions we can discuss. E to the minus I e of k1 e over k square. Psi of k1 of x dk1, right? And if you sort of write this out in all its glory, then it's going to look like this. This is just okay. ठीक है भाई, ये dk1 psi k ये आ गया और ये वहां से आएगा, ये जो लिखा ठीक है, एक ए से आएगा, ये एक ए है, ठीक, ओके। अच्छा, पहली टर्म क्या है? इसको ले और इस सारे को अगर आप गौर करें ना, इस सारी चीज को भूल जाए थोड़ी देर के लिए, इसको इसके साथ लिखें, आपको नजर आएगा कि ये e to the ik1x है ना, this is the inverse Fourier transform of what? Of this thing. Where did it come from? It came from there. So except for this factor, इस factor के अलावा बाकी क्या है? ये inverse Fourier transform है initial wave packet का, ठीक है? और ये क्या आपको देता है, ये और ये आपको कहता है कि अब जो आप बेसिकली इस तरह से है k1 x प्लस a। सो पहले आप माइनस a के ऊपर थे, अब h कट k1 t ओवर k0 t ओवर n, अब आप यहाँ पर हैं। सो अगर आप अब हमने किस लिमिट में हमने इसको देखना है, लिमिट t गोइंग टू इंफिनिटी। सो जब t goes to infinity, the center of the wave packet, initial wave packet, is where? At somewhere here, right? लेकिन इसके साथ मल्टीप्लाई क्या हो रहा है, theta minus x, so this term is 0. So the initial wave packet in the limit t going to infinity has just withered away. It has gone away. It is no more. बात समझ आई? ठीक है, अब आप इसको देखें, ये क्या है, ये है माइनस एक्स माइनस ए। सो ये वेव पैकेट प्लस ए पे है, पर इट्स मूविंग टू दी लेफ्ट। सो इन द लिमिट t गोइंग टू इंफिनिटी, it is, अगर आप इसको sort of at k1 या k0 निकाल के इसको बाहर निकाल लो, तो बाकी चीज क्या है, बाकी अगेन इनवर्स फोरियर ट्रांसफॉर्म है, आपको एक गाउसियन देगा, but that Gaussian in the limit t going to infinity will be located somewhere here. So this is your reflected wave packet. Okay, ये बात समझ आ रही? So psi of r, अगर मैं psi of r को लिख दूं, so psi of r will be some this theta of minus x, b over a बाहर निकाल लें at 0, ठीक है, और फिर बाकी जो चीज है वो रह जाएगी Gaussian at a minus k naught। अब आपने इसका स्क्वायर लेना है ना और निकालना है, r निकालना है, तो r क्या होगा, r इसके नीचे तो एरिया 1 होगा, इसके नीचे एरिया 1 होगा, this is nothing, so what you are left with is b over a, ठीक है, and this thing is equal to e naught minus e naught minus v naught 1/2 over e naught 1/2 plus e naught plus 1/2। हाँ जी, ठीक है, राइट। और अब आपको पता है कि t plus r is 1, so t is 1 minus r, 1 minus r। So our problem was, given psi I, we had to calculate r and t, and we have been able to do that only because we chose a wave function that was highly peaked in the momentum space at k0. If we hadn't done that, it would be very difficult for us to separate out these two things very cleanly. ठीक है? अच्छा, ये बात तो ठीक है, लेकिन मुझे 1 dimensional scattering करनी नहीं है, मुझे तो 3 dimensional scattering करनी थी। So why am I doing this? इसमें एक बहुत बड़ा लेसन छुपा है। वो लेसन ये है कि आप ये देखें, you didn't have to do all of this, आपको ये करने की जरूरत नहीं थी। क्यों जरूरत नहीं थी भाई? इसको देखें, पहले आप psi of k naught ले लें, जो मोमेंटम का आइगन फंक्शन है, ठीक है, लेकिन एट के नॉट, इसमें मसला क्या था? इसमें मसला ये था कि ये आपको एक प्लेन वेव देता है जो आपको ये पिक्चर नहीं देती कि एक वेव पैकेट आ रहा है, वो टकराता है, फिर टूट जाता है, और फिर आप रिफ्लेक्टेड और ट्रांसमिटेड वेव के प्रोबेबिलिटीज कैलकुलेट करते हैं, राइट? इसमें ये मसला है, लेकिन एक इसमें बड़ा एडवांटेज है, वो आप देखिए, इसको मैं लिख सकता हूँ ना, a naught e to the I k naught x plus b naught e to the minus I k naught x theta of minus x plus c naught I k naught square minus 2m v naught over h naught squared x theta of x, right? Calculate Ji. याद है ना? Probability current, right? Calculate Ji. Ji is a naught squared h cut k naught over n. J reflected is b naught squared h cut k over n. अच्छा, रिफ्लेक्शन कोएफिशिएंट था क्या? वो था a b naught over a naught squared. But what is this equal to? This is simply Ji over. Sorry. Yeah, Ji over. No, Ji over Ji. हम 3 डायमेंशन में ये करेंगे और t हमें पता है 1 माइनस r है, राइट? और वो बेसिकली आप शो कर सकते हैं कि वो c नॉट ओवर a नॉट स्क्वायर और यहाँ पर आगे कुछ आएगा और चीजें। लेकिन बेसिकली ये देखें, बहुत सिंपल सी बात कि अगर आप अपनी उस पिक्चर से दस्तबरदार हो जाए ना कि जिसमें एक वेव पैकेट आता है, वो टकराता है, वो टूट जाता है और आपको बहुत कॉम्प्लिकेटेड एनालिसिस करना पड़ता है, आपको कहना पड़ता है कि मोमेंटम स्पेस में आपने बड़े पीक होना है और फिर आपको उस लिमिट में 2 पैकेट मिलते हैं जिनसे आपको निकालते हैं। उसके बजाय आप वो काम करें जो शुरू में करना चाहिए था कि मोमेंटम की आइगन स्टेट ले लेते, ठीक है? एनर्जी की आइगन स्टेट से यहाँ पर जो भी है मोमेंटम की आइगन स्टेट को समझ लेके आए के नॉट के ऊपर ये पीक है, राइट? और इस आइगन स्टेट में ये चीज रिकग्नाइज कर लें।
सर मोमेंटम की तो ली थी हमने k डॉट पीक।
मोमेंटम की आइगन स्टेट तो नहीं थी, था तो वेव पैकेट, अगर आप वो ले लेते तो आपके पास वो पिक्चर नहीं होगी आपके कोई चीज आ रही है, वो टकराएगी, उसके बाद वो 2 टुकड़े होगी, फिर आप उनको कैलकुलेट करेंगे। जो इंसिडेंट वेव है, जो रिफ्लेक्टेड वेव है और जो ट्रांसमिटेड वेव है, दे एग्जिस्ट फॉर ऑल स्पेस एंड फॉर ऑल टाइम, ठीक है? आपके पास वो उस तरह की क्लीन पिक्चर नहीं है जो आपको क्लासिकल मैकेनिक्स में थी, लेकिन ये चीज आपको रिफ्लेक्शन कोएफिशिएंट दे देती है। So, जब हम 3 dimensional scattering करेंगे, that's what we'll do. We will calculate the eigenstates of the Hamiltonian, और उन eigenstates में हम एक momentum की eigenstate, एक particular momentum लेके उसमें हम recognize कर लिया करेंगे कि reflected part कौन सा है, और जैसे हम यहाँ पे कर सकते थे, मैंने आपको एक बताया था, यहाँ पे देखें, ये incident part है, ये reflected part है, ये transmitted part है, right? तो हम इस तरह से उसके अंदर ही रिकग्नाइज कर लिया करेंगे और जो आपके करंट की रेशियो है वो आपको कोएफिशिएंट देंगे।
k is not equal to k dot की सारी वैल्यू 0 कर दी थी, नहीं
की ना, अप्रॉक्सीमेटली। अगर वो हम ना करते, अगर हमारा डेल्टा लार्ज ना होता, अगर ये हमारा डेल्टा लार्ज ना होता तो फिर k नॉट से अगर आप दूर भी चला जाएगा आपका k1 तो ये कुछ इसकी वैल्यू रहेगी, सब्सटेंशियल रहेगी। सिर्फ इस लिमिट में कि डेल्टा स्क्वायर बहुत बड़ा हो, जैसे ही आप k नॉट से थोड़ा सा भी दूर जाएंगे ये एक्सपोनेंशियल इसको फौरी तौर पर खत्म कर देगा, ठीक है? लेकिन स्टिल अब हम कह रहे हैं कि वी आर एग्जैक्टली एट k नॉट। पहले हम ये नहीं कह रहे थे, पहले a k1 इज नॉन जीरो फॉर एनी k1 एक्सेप्ट इज एक्सपोनेंशियली स्मॉल।
तो पहले हम ना पोजीशन के आगे स्टेट्स में
ना मोमेंटम की आगे स्टेट, राइट, सॉर्ट ऑफ मोमेंटम की आइगन स्टेट है हैमिल्टोनियन की आइगन स्टेट, लेकिन चूंकि पार्टिकल लेवल इनिशियली भी फ्री है, फाइनली भी फ्री है, सो वी कैन जस्ट सॉर्ट ऑफ take the reflected wave and the transmitted wave and just match the conditions with the initial wave.
हम हैमिल्टोनियन के आइगन स्टेट्स में थे, इधर हम मोमेंटम के
ये हैमिल्टोनियन की आइगन स्टेट थी, चूंकि पार्टिकल इनिशियली भी फ्री है, फाइनली भी फ्री है, तो इस सॉर्ट ऑफ मोमेंटम की आइगन। तो हैमिल्टोनियन की आइगन स्टेट लिख के उसमें इंसिडेंट वेव, रिफ्लेक्टेड वेव और ट्रांसमिटेड वेव आइडेंटिफाई कर लेते हैं। ठीक है? So this picture will not have the sort of benefit of the being intuitive the way a classical picture is. Something comes in, strikes, and then sort of reflect, it goes in some direction. Lekin this will just generate by results.